So the Big Bang is a term associated with the very beginning of things, the very beginning of time itself. Matter, energy, space, and time all together. And in this little region here, I show time equal to 0 seconds. And that's what it corresponds to. Temperature, energy, density. Are these really infinity? They are referred to in terms of infinity for these physical characteristics. But we really don't know, as has already been mentioned. But we do know it's an incredibly structured expansion of the universe, because from it emerges everything as we know it today. The emergence of the laws of nature themselves, the ability to do science, comes from this event. So science can't really penetrate the origin of that event because from it comes the ability to do science. You see the logical problem there. Now, we don't understand the physics of the event, so when you hear some erudite scientists discussing in very eloquent terms what took place at the beginning and referring to these infinities, recognize that's really a statement of ignorance because we don't have justification for saying what things actually were like at the very beginning, because we don't have a theory to describe it. So I've probably said that enough times at this point. Then we enter into the Planck era, or the quantum gravity era, 10 to the minus 43 seconds, 10 to the 32 Kelvin. It's the closest theoretical point to a beginning of time that we can really discuss, having no theory to describe what takes place prior to that. Space and time, energy, gravity, they're all intermixed. But there's huge quantum gravity fluctuations, which are somewhat mysterious to us because the densities are so great as well. So quantum mechanics and general relativity, gravitational concerns are all there together. All four forces are joined into what's understood as being a superforce, as we discussed as well. And the particles and everything that's going on there is all in thermal equilibrium. Then at 10 to the 32 Kelvin, gravity freezes out, kind of like ice crystals that form as liquid cools. Takes a lot of energy removed from the system to bring liquid into the solid phase. So that's an analogy. And that ends the Planck era. The Planck era ends and it enters into the grand unified era, where that's associated with the other three forces still being unified. Now, I probably should have already mentioned this as we go through some of these details. Don't pull your hair out thinking that you have to know all the specific details of these different eras. Just trying to give you a foundation, an overview of the process so you have a greater appreciation. But you're not going to be tested on the temperature of the grand unification era, for instance. That kind of specificity is not what I have in mind. So just relax a little bit and try and get the feel of the broad picture. We are now in the grand unification era, though. 10 to the minus 35 seconds, 10 to the 27 Kelvin. It's the unification of the other three forces. This graphic over here is a little bit irrelevant. I suppose in that sense I shouldn't have put it in there. There is no picture, no visual picture that can express the reality, because in that case you'd be talking about photons bouncing off of materials and producing an image on your retina. No such thing even exists, so there is no accurate visualization. So kind of ignore that. But if you're the kind of person that likes a picture associated with the words, there it is. So the four fundamental forces were a single super force during this time. Then gravity freezes out. Here's the freeze out of gravity. Notice the temperature scale here, the time scale up above, 10 to the minus 43 seconds. And at the end of the grand unified force era is 10 to the minus 35 seconds. So at that point, we have the separation of the next force, which is at 10 to the approximately 10 to the 29 Kelvin, the grand unified theory force. The synthesis of these three forces no longer is intact, and the strong force splits off. So we have the strong force and the electroweak force remaining. Now this era lasts a trillionth of a trillionth of a trillionth of a second, and not well understood or tested, but the forces that are diverging at this point may have provided the energy to propel what we call inflation. And we're going to spend some time on inflation and come back to it a time or two as well in subsequent discussions. So now the inflationary era, starting at about 10 to the minus 36 seconds, associated with a burst of dramatic, tremendous expansion beginning, and the universe doubling in size about every 10 to the minus 34 seconds, and it's over by 10 to the minus 32 seconds. All these time frames are shorter than what's comprehensible. So it's in this small era of time here. And what's going on then? Well, the strong nuclear force freezes out, and very small quantum fluctuations in the fabric of space-time at that point can literally grow to the size of the solar system. Now don't be too concerned if you're a very detailed person. You might have seen some inconsistencies in statements about the inflationary era, when it begins and ends, and how many times bigger the universe becomes over that interval of time, depending on what textbook you're reading or what study you're looking at. It's something that isn't very well understood, and that can be seen by the fact that there's different estimates for this based on different formulations of the theory, the mathematical theories that undergird this theory. So the point is that there's a massive increase in the size of the solar system, many orders of magnitude, and that has huge implications for the subsequent development. The energy from inflation can then actually, potentially, lead to the production of matter. E is equal to mc squared. We can get energy producing matter. So that means, in this case, particles. Next is the electroweak era. Begins with gravity, strong electroweak forces in operation on this graph again. And at this stage, things are hot enough that there's a quark gluon plasma, too hot for quarks to clump in together to form protons. Currently, it's very difficult to separate quarks because of the energies associated with that event. But at this stage of the universe, you couldn't get them together. So up to this point, photons, very, very energetic, and matter-antimatter particle pairs can interchange with each other. Because we have gamma ray photons that are so energetic, they can produce quark-antiquark pairs, which then subsequently come together, annihilate, and produce gamma ray photons again. So it's a process of annihilation and synthesis of the, so to speak, of the particle pairs. But then as the temperature cools, as time goes along here, temperature is cooling very rapidly. The photons eventually are too weak to produce these quark-antiquark pairs through E is equal to mc squared. The quarks and antiquarks annihilate each other, but there's a slight excess of regular matter over antimatter to the extent of about 1 part in a billion. And that's a little bit mysterious, but very important at the same time. So that's the state of the universe at that point. Then the electromagnetic and weak forces separate at the end of this era. Therefore, we have all the 4 known forces of nature distinct from about 10 to the minus 10 seconds or so right up to the present time. Now, the universe is still about 100 times hotter than the core of the sun, so incredibly hot still. It's important to recognize that at this stage of the theoretical development, we actually have empirical evidence. In fact, in 1983, CERN, particle accelerator, was able to reach the energies and temperatures associated with this unification of the electromagnetic and the weak forces. So it was able to detect the kind of particles that should be produced in the interactions going on in those conditions. Why is that important? Because that tells us exactly that what we think the universe was doing indeed is. In other words, there's direct evidence of the conditions associated with these temperatures. So from this point onward, we have direct evidence for the theories. Prior to this, it gets less and less certain, all the way back, I should say, to the Planck time, where we're very uncertain about what's going on. So, going forward, we have very high empirically based confidence in our understanding of the universe. We now enter the particle era, about a millisecond after the origination event, and we're at a temperature of about 1 trillion Kelvin. At this point, the photons don't have enough energy to produce the quark-antiquark pairs, so that quark-antiquark annihilation has to stop. So there's no more production. They annihilate each other, but somehow about 1 in a billion quarks is left behind, not antiquarks. That's a big mystery, very important too. The remaining quarks combine into protons and neutrons. This is the fundamental matter, fundamental normal matter that we're used to. And they start sharing the universe with the other fundamental particles of electrons, neutrinos, weakly interacting massive particles. Now, the lower mass electron-positron pairs, which is an electron and anti-electron, they can still be created and destroyed because they take less energy. They're less massive. It's called particle pair productions. We can have a nucleus and a gamma ray photon producing these, in part, electron and anti-electrons, or positrons, which will subsequently annihilate each other and produce photons again, and other combinations of particles and photons. It is very strange and not well understood as of yet phenomena, what we call symmetry breaking. There's a lack of symmetry between the regular matter and the antimatter. So the present universe that we have has about 1 billion photons for every proton. Okay, gamma ray photons. So that means that for every billion antiprotons that we started out with, there was 1,000,000,001 protons. So after the annihilation took place, the billion particle pairs producing photons, a single proton was left over. So the universe we have now at our disposal is just a tiny little remnant of regular matter that was left after the matter and antimatter, which was almost the whole thing, annihilated each other, producing energy, producing photons. Very strange reality. At about 1 second, we have what's called neutrino decoupling. Now, we all know that, hopefully, that neutrinos are these mysterious little entities that don't interact very much with regular matter. But the flux density, the density of the neutrinos in the early stages, was so great that it had a huge significant impact in the universe. But after about 1 second, they no longer interact significantly with matter because of their relative density. In addition, the photons can finally no longer produce the electrons and positrons, so that ceases, and we're left with about 1 in a billion electrons, just like there was 1 in a billion protons left over after the matter-antimatter annihilation was over. We now enter into the era of nucleosynthesis, and we're talking about minutes instead of seconds or milliseconds, so this is something that's a lot more comprehensible to us. And the temperature is about 1 billion Kelvin rather than 1 trillion Kelvin as it was in the particle synthesis that we just discussed. And so far, everything has happened in just a millisecond, less than the blink of an eye. And hydrogen, which is just protons, they've existed now for some time. But as they try to fuse and produce heavier elements, based on the energy they have the energy to do so, but they get broken apart as fast as they form because of the energy of the photons. So really this era is a time that's characterized by fusion and demolition, or fusion and fission, of the particles. But eventually the photons no longer have the energy to bust apart the deuterium, the proton and neutron formation, so they stick together. By the end of 3 minutes, helium is sticking together. At this point, the universe is about 75% hydrogen, 25% helium. Interesting. That's the same as our present proportions of hydrogen and helium, which is strong evidence for the Big Bang. This discussion that we're having right now is Big Bang theory, consistent with what's going on with the Big Bang, which is consistent with what we see in reality in the universe. So that's strong evidence for the Big Bang. Very tiny amount of lithium produced as well. Now, the temperature is too cool to continue to bring the nuclei together and fuse them. So we don't have hydrogen producing helium, so that fusion stops. But the temperature is still too high for the nuclei to grab a hold of the electrons. So atoms? No, no, no. We don't have atoms yet. We just have nuclei. The energies associated with nuclei versus actually holding on to electrons is quite a big gap. So electrons and nuclei are basically just swimming together in a plasma soup at this stage. Temperature is about 1 billion Kelvin. At this point, the universe enters into a relatively stable phase in that the nuclei that are formed are not going to grab a hold of electrons for some time. There's too much energy in the photons still to enable the electrons to be captured. We are in a radiation-dominated universe, which is going to be true for 30,000 years. The photons prevent the collapse of matter, so you don't have any stars or galaxies forming. A transition is going to take place at this point, because up till now, the photon density has actually been greater in terms of its gravitational effect than the matter density, the actual mass. According to E is equal to mc squared, energy and mass are equivalent, and so the energy of the photons is so great that it has more gravity than the matter. It seems really strange, nevertheless true. So the photons can gravitate, but they also exert an outward pressure to keep the matter from collapsing, from the matter density and the photon density. The outward pressure is greater, so no collapsing occurs. So matter density is decreasing, photon density is decreasing. They're both decreasing at the same time, but the photons are not only spreading out, but they're losing energy as well. So the photon effect is diminishing more rapidly, which is what's responsible for this crossover that occurs at about 30,000 years. So the matter at that point begins to clump together, and this is the transition known as the transition from radiation to a matter-dominated universe. Even in the condition of matter domination, the photons still outnumber the nuclei 1 billion to 1, but they're of less energy. They don't have the same impact as they previously did. So we have a matter-dominated universe, and in this chart we see another phenomena here about dark energy, which is another topic. But nevertheless, this is the major transition that occurred at 30,000 years in the history of the universe. So at the end of 5 minutes, the universe consists of primarily hydrogen and helium nuclei. And so we have a soup, a sea, of protons, electrons, and photons mixed together in a hot plasma. And from 5 minutes to about 380,000 years, we have the condition where the photons are scattering off the electrons, bouncing from one to the next. And in so doing, they don't escape from this soup. And in the interim time, between 5 minutes and 380,000 years, we just discussed that 30,000 years, the transition from radiation to matter domination. So this era of nuclei spans right through that time, all the way to 380,000 years. And it could be considered a primordial fireball, the universe, because the light, the photons aren't escaping. So you have this ball, so to speak, the whole universe, all contained by, well, it's not the whole universe, but the particles and photons there, not necessarily the space. The particles within the universe being a fireball that's contained. So that's one way to think about it. Now, by 380,000 years, the electrons were so spread out that the photons would miss them, and also the energies are so low that the photons don't have enough energy to ionize the electrons that are grabbed by the hydrogen nuclei, and you first now form atoms. So for the first time, nuclei can hold the electrons, neutral hydrogen is produced. This is known as recombination or decoupling. Those two terms sound a little bit odd put together. Recombination, in the sense that the electrons are now first joined with their protons to produce atoms. Decoupling in the context that the photons decouple from the atoms. So these stretched out lower energy photons are now free to escape the confinements of the plasma where they were previously confined. So they are decoupled. So the universe becomes transparent. Light can get through it. And the photons that escape, they should have the signature of a 3000 Kelvin blackbody known as the cosmic microwave background radiation, CMBR as it's abbreviated. This is a very, very important transition point in the history of the universe. And then it's followed by the era of atoms, which is simply the end of the era of nuclei and the beginning of the point where the electrons are held by the nuclei. So we have neutral atoms, plasma, photons all together in a mix. So in the next part, we're going to look in more detail at this cosmic microwave background radiation because it plays such a prominent role in our understanding of the universe.